All right, so we're going to go over the alkali metal problem set. It's recorded, so you'll be able to watch it and slow it down if you need to. I'm going to do argon and krypton. So this is where you need your periodic table. Know that the left side, you start your energy levels with 1 and you go all the way down to 7. When you go onto the right side, your energy levels start at 2. Right, energy level 2 with neon, it goes all the way down to 6. Radon, the UUOs are not actual elements that have been discovered yet. In the middle, we have 10 electrons that represent our d orbitals, and they also start numbering a little bit different than our s orbitals. They start at 3, 4, 5, and 6. And then the f orbitals down there in the lanthanines, they start with your energy level 4 and go to 5, and they have 14 possible for that. In the practice, there wasn't any f orbitals. Not that I'm not going to give one of those on the test. However, in the practice, we kept with the sets all the way up through D. So I'll start with argon. Argon, as you go through, you're going to have the first energy level. You fill the second electron. You go to the second electron. I'm sorry, second energy level. You fill 2 electrons in the second orbital. You're still in the second orbital energy level, but you're filling the p orbitals 6 electrons. You have another, because right now we're only at neon. So we're going to go to the third energy level. We're going to fill the s orbital completely, 3s2. Then we're going to go to the third energy level, continue on with that, and fill the p orbital completely. So now we're all the way over to argon. So on the periodic table, we're all the way over to argon, all the way over to the right. It is considered a noble gas, so maybe I'll make note of that right here. We are a noble gas. Then if we're going to krypton, well, your krypton is actually only one more proton from argon. So our beginning is going to be identical, and that comes into play in our discussion further down. So we are now at the point where we are argon again. And now we're at the 4th energy level, s orbital, but we've only filled 1 electron. This is going to come back in our discussion when we discuss the similarities and differences between these 2 elements. All right, so with that note, I'm going to go down to our discussion questions. Let's focus on our discussion. It says, look at the electron configuration you've written below for the elements Li, Na, potassium, rubidium, and cesium. And I didn't include francium on that one. I'm going to label these. These are all called alkali metals. There's a name for these. So that whole column, they're called alkali metals, including francium, which is the last one. And then our first one is hydrogen. Hydrogen's a gas, so it's not considered an alkali metal. What similarities do you notice between these configurations and what differences? So I'm going to note similar and different, since I've asked you to discuss both of them. Differences. Okay. So similarly, all of your alkali metals, so every one of these, rubidium, sodium, they all have a valence shell of 1 electron. So all these metals, so all alkali metals are filled with the s orbital of 1 electron. Okay, so their valence shell, the last shell, valence shell electron, is 1. You know, 1 electron in its last shell. The differences are that as we go down, here I'm going to refer to the periodic table, as we go down, your energy levels are increasing. Okay, that's when we discuss the numbers. Okay, they go 1, 2, 3, 4, 5, 6, 7. So a difference between all of them is, although they share 1 electron in this valence shell, the energy levels are increasing. So from Li to cesium, they're increasing. So I just pointed out which ones were increasing. Let's look at the second discussion question. It says, look at the electron configuration you've written for these elements. I'm going to label those because we've discussed that before. They're called noble gases. And gases can be spelled with one S or two. I did look that up because everyone spells it a little different. What similarities do you notice between these electron configurations, and what can be said about how full the outermost energy level is in each configuration? Well, if you notice the electron configuration of your noble gas, and I'm going to pull it up right here, this is the energy level. Its energy level has 8 electrons. So what we can say is that they, and by they I mean all these noble gases, they have filled the valence shell. And I'm going to just reiterate how we know that. Your s orbital and your p orbital giving you 8 electrons in the valence shell. All right. So when we're looking at noble gases, we discussed how they are unreactive because they have full energy level or full electrons, valence electrons. Let's look at number 3. So discussion question number 3 says, look at the electron configuration in each of the pairing. So you're looking at the noble gas and the alkali metal. Noble gas and alkali metal. What are similarities and what are differences? So let's take a look. I'm going to write similar and different. I'll just put 3 dots there. All right, well, they're different, and I'm going to refer just to the one that we've done, but if you look at this, they're different because our alkali metal has another energy level and 1 electron in that orbital. So 1 more electron in an energy level. So you have 1 more energy level. So at this point, I'm just going to shorthand energy as capital E with an s orbital for your alkali. Versus, I want to compare them when I'm talking about differences, versus your valence shell is filled with sp 2 and 6, indicating 8 electrons in the noble gas. Well, let's take a look at what could be similar about this. Let's take a look. Well, if you look at this, a big thing that you'll notice is that both of these elements, and it goes hand in hand for all of these pairing, but I've done this example. So if you look at the fact that we have argon represented in both of them, so both of them do show the majority of the similar is that the fact that they showed the actual configuration. So your alkali metals share a similar electron configuration as its noble gas prior. Just pretty much the reason why we can use our noble gas configuration in our shorthand. So I could use argon in my shorthand and continue to make our next one, which is the alkali metal, which is just adding 1 more atomic number. All right, we've got 4. Let's take a look at number 4. Discussion number 4 reads, draw an orbital. How will the size from 1s orbital compared to 2s orbital? And below, draw a rough representation all the way up through 6 energy levels. So I'm going to draw 1, and again, because I'm inking it, I apologize that this is so sloppy. So I have 2 energy levels, and then I have 1, 2, 3 energy levels, 1, 2, 3, 4 energy levels, 1, 2, 3, 4, and 5 energy levels, 1, 2, 3, 4, 5, and 6 energy levels. Whew, there you go. So I've just drawn them. I've depicted what they look like. Again, the large number is the energy level, and then I've got the, I just put the orbitals. So if it's an s orbital, I can also look and see if these are all your alkali metals were the examples. So even in the s orbital, you're only having 1 electron if these are the examples that we gave, alkali. So I've added that to it too. So alkali metals only have 1 electron. That's I'm going to refer back to this image for the next 2 discussion questions, because it says, look in the sketches, number 4. What can you say about the separation between the nucleus of an atom and its location of where your valence electron is? That's basically what all that writing said. So if you're looking at the nucleus, I'll color it here. You're looking at the nucleus. I'll color the nucleus in green. Okay, back to purple. And you'll notice that my electron here in the 1s, positive nucleus with a proton, negative electron. Your 1s, although it only has 1 electron, it can easily be taken away. So don't doubt that that reaction doesn't happen quickly. We saw that from the video. It does happen quickly. However, you have a stronger hold on that electron. Let's look at that 6s. That green represents the proton and neutron, so that positive proton. And that purple dot represents that 1 electron. And you can see how many energy levels away it is. So when it's really trying to grab a hold of that 1 electron, it really doesn't have a good hold on it. So those electrons can be ripped off really easily. So that's why in that video that you watched of the reactions with water, as you went down, let me bring my periodic table out. As you go down from lithium to cesium, your reaction, and potentially they gave you the example of what francium would look like, your reaction would happen more and more and more vigorously, because the electrons can be taken off easy. You don't have a good hold on it. So the further, I'll write this up here for you, the further away from the nucleus, there are more energy levels. If you have more energy levels, the positive nucleus does not have a strong hold. And then it asks you to put in order from the toughest to the easiest to remove. Again, understand that all of those with 1 electrons are a lot easier to remove than, let's say, even the second S2 category or further in. But when we're comparing just in that column, we can say that Li has the toughest to remove electron, and then Na, and then K, rubidium, and then cesium is our example, our last one here. And it has the easiest to remove the electron. Okay, then we're in our last discussion question, number 6. All of these elements, these alkali metals, including francium, which has such a short half-life, so you really can't get a hold of it, they react vigorously with water. We know that, we saw that. They're still way more reactive than even column 2, group 2 elements. But when we're looking at them, again, comparing just the row, you saw this in the video. Explain why potassium reacts more vigorously than sodium does. Well, if you look at potassium and you're looking at the periodic table, you'll notice that potassium has 4 energy levels versus sodium that has 3 energy levels. So you can quickly draw that 1, 2, 1, 2, 3, and I'll just put sodium. I'll just draw that last energy level electron, and then you have 1, 2, 3, 4. And that is our example for potassium. Again, I'm going to show you where the nucleus is. Oops, my little dot is a little bit sloppy. I apologize. So when it's asking you, what can you say about the relationship between the ability to lose the electrons and the rate of reactivity? Well, it's easier to lose, even easier than sodium. Still, that both can lose easy, but this one is easier to lose because it's further away from the nucleus. It doesn't have a strong enough hold compared to sodium. So when you're asked to discuss that or write that up in an answer for the exam, you want to make sure that you've shown me that you understand by drawing a depiction of the picture, and also in writing, you want to explain like how our discussion question is right now. So I'm going to pause the recording